Namaskar and welcome back to the course on statistical mechanics of phases and phase transitions. We have completed the chapter on scaling, renormalization, and also looked at real space methods. Today we are going to start a new chapter. This is going to be an exciting chapter, and we are going to look at one of the landmark formulations of theories of physics, which is the Wilsonian renormalization group idea. So, we will start with a quick recap of the renormalization group idea itself, which is, as I am presenting it, was formulated by Wilson. So, the starting point of the renormalization group idea is that systems at criticality have an emergent arena symmetry, which is scale invariance. Scale invariance is characterized by a transformation which requires a scale factor which we take it to be greater than 1. So, S is greater than 1, the scale factor, and what this does is it allows you to think about coarse graining, which is that you are sort of looking at the system on larger length scales. And what the scale transformation does is it of course changes the coordinates in the way that we write down here, but will also change the Hamiltonian. And if you think of the Hamiltonian as something like a Ginzburg-Landau theory with all possible symmetry allowed terms and whatnot, then this Hamiltonian can be thought of as a point in the space of theories, in the sense that you collect all the coefficients of the different operators that go into the Lagrangian density, and you collect them into a point P, and the idea now is the scale transformation that you are performing will change this point to a new point which is P prime, which we write as P of S, because the point P prime will be determined by S, the factor by which you are scaling. And this transformation, which is called as the renormalization group transformation, is formally denoted by this thing called as Rs of P, and it induces a flow in the space of theories. Space of theories is a set of all points P which characterize the coefficients of, let us say, the Ginzburg-Landau theory. So, the critical points and also phases, as we saw in the last meeting, are described by fixed points of the renormalization group transformation P star, which are invariant under the scale transformation. So, Rs of P star will be P star itself. To obtain the critical properties around, let us say, a critical point, what you do is you explore the properties of the linearized renormalization group transformation, which is characterized by a matrix Ls of P star, and this Ls of P star will have a set of eigen operators which are indexed by some label I, such that Ls of P star acting on OI, so there is an OI missing here, will give you S to the mu I, S to the power mu I OI, where this mu I is called the index or critical exponent associated with this operator OI. Now, the eigen operators OI are said to be relevant if mu I is greater than 0, and irrelevant if mu I is less than 0, and marginal if mu I is 0. What that means is, if I write an operator with some coefficient Gi, as I do the scale transformation, the size of the coefficient will grow if mu I is positive, therefore it is relevant, and irrelevant it will go to 0, and marginal it will not change. So, the origin of universality and scaling hypothesis, all of these arise from the fact that there are a few relevant operators, and once you have only a few relevant operators about the critical point, then the system forgets a lot of details, because it is going to be governed by just these few things, the few operators that are relevant. And from there you can both understand universality, as well as if you look a little deeper, you will also realize that the free energy, the singular part of free energy, is a generalized homogeneous function of these relevant operators, and therefore the scaling hypothesis, as was sort of postulated to understand the critical properties, they will be the scaling hypothesis will come out as an outcome of this idea. So, we have looked at the real space implementations of RS, and real space implementations of RS showed us how RG works, we were able to actually extract these mu t and mu h, etc. for the Ising model, for example, and we were able to obtain critical exponents. So remember, it's not just a conceptual idea, it's also a calculational tool. We can extract critical exponents. The unfortunate thing about these real space methods, although they are very intuitively appealing, they have certain uncontrolled approximations if you want to take the calculations through, and it's not quite clear how we would improve on them, right? So there is no natural way to improve on these ideas. So this was the state of affairs, let's say in the late 1960s, and this is when Wilson explored this problem in great depth, and he was able to come up with a very unifying set of ideas which we have already seen, and he was also able to come up with a method for doing these calculations which is very systematic in the sense that it can be applied to a large class of problems, and this is what we are going to discuss in this lecture. Okay. So this Wilson did variety of types of renormalization group. The primary one which has become very popular and which has been used extensively in all areas of physics is the field theoretic way of doing renormalization, and this is often also dubbed as momentum space RG as opposed to real space RG, which is what we saw in the last lecture. Okay. So what is the idea of this Wilson's framework or formulation? So what we do is we start with a continuum arena. So we are in d spatial dimensions with coordinates described by this x, and we start with a phenomenological field theory like the Owen-Ginsburg-Landau theory, which we have extensively studied in previous lectures, and the fields are some Owen vectors, and we work in the thermodynamic limit. We always work in the thermodynamic limit because, as you know, if you work in a finite system, you will not have any singularity of the free energy. So we have to work in the thermodynamic limit, and I will try to indicate where this thermodynamic limit will become important. So very important thing that was well appreciated by Wilson and really emphasized by him is that all such phenomenological field theories, they always come with an ultraviolet cutoff length scale, which we call as little l here. So this could be like a lattice parameter or some slightly coarse grained length scale, but typically an atomic length scale, at least in the context of the problems that like magnets and so on. They can be some other unknown length scale if you think in terms of field theory of elementary particles and so on, or we can also use a different way of thinking about this is that there is a cutoff in the momentum space or in the wave vector space. That is, you say that there is a lambda which is sort of inversely proportional to this L. You can, both are equivalent ways of thinking. So there is either a momentum cutoff, and since we will be working in momentum space primarily, when we say cutoff, we typically will mean now momentum cutoff lambda, capital lambda. That is our notation. It's a pretty standard notation. Okay. Now, as we already discussed, phenomenological theories will be described by a set of coupling constants. So you collect all these coupling constants into a big vector, and that vector the set of all such possible vectors will span some kind of space, and that is the space of theories. And this P, some typical point P, there is where we have our theory. We maybe do some experiments, we figure out some starting point of the theory, and that is the theory we would like to study. So the emphasis of Wilson's method is to understand the physics of the long wavelength modes in the system. Why is that important? Because Wilson realized that what we observe on the longest length scales are the modes of the system whose wavelengths are very large compared to this L, right? So those are the modes that are actually what we are observing near a critical point when we do experiments and so on. Primarily, all the critical properties are actually governed by those. So he chooses naturally to work in the momentum space, and use Fourier components of the fields. And the idea is that in momentum space you can distinguish between long wavelength and short wavelengths by looking at the value of the wave vector. Okay. So the transformation RS is implemented in Wilson's method in 3 steps. So we will see this many times so that it gets internalized in us. So the first step in Wilson's idea would be to integrate out the short wavelength modes. So when I would like to immediately connect to what we did in the real space method. So in the real space method in 1D Ising model, for example, we integrated out the odd sides, the spins on the odd sides. But you see here we are not integrating out real space degrees of freedom, we are going to integrate out modes that are between lambda by s. Remember, s is the scale factor. Let us say s is say 1.1 or something. So let us say 1 by s is 0.9, let us say. Then from 0.9 lambda to lambda you have modes, Fourier modes, whose, if you look at what they are doing in real space, if you inverse Fourier transform them, you will see that they are fluctuating very strongly in the sense that their wavelengths are 2 pi by lambda, which is of the order of L. So they are fluctuating on the odd scale of order L. So the idea is that when we observe the system on long wavelengths, we sort of coarse grain over them. So we would like to understand what is the effect of this coarse graining on the long wavelength modes. So that is what we do by integrating them out, and once you integrate them out, you will see that the cutoff of the theory reduces to lambda by s. So you have sort of gotten rid of all the short wavelength modes and you have changed the cutoff to lambda by s. Okay. But then you will say, okay, but that is a problem, because how do I, if I want to see whether this theory is scale invariant and I have this lambda and I reduce the lambda, then the new theory that I am going to develop cannot be compared with the previous theory because they have different cutoffs. So the next idea is to rescale the coordinates and momenta by the scale transformation that we want to implement. So what happens here is the new coordinate will be x by old coordinate by s, and the new momenta or the wave vectors will be s times k, just the inverse of this because they have a relationship. And what this does is it restores the cutoff back to lambda. And now what we do is we introduce a new set of intermediate fields, where after integrating out these fields, we will have fields with longer wavelengths, which means that only smaller momenta from 0 to lambda by s. We introduce these new fields, and based on this transformation, we will introduce the new fields in this new scaled coordinates. So now we get a field which has, in the new set of coordinates, has cutoff restored back to lambda, and there are these intermediate fluctuating fields. Now why is this called intermediate? The true new fields will be determined in the third step, and the third step is to renormalize the fields. So what we are going to do is we are going to take these fields and multiply them by a factor which depends on the scale s in such a way as to meet a certain criterion called as the renormalization condition. Okay. So this is the 3 steps, and I will be the first to admit that if you are seeing this for the first time, this look a little bizarre as to what is going on, what is all this integrate, rescale and renormalize. So let us just familiarize with these terms, and then what we will do is we will look at examples and we will see what they are doing. The outcome of this whole story is that you will find that the coupling constant you started off with will change to a new set of coupling constant. The form of the action will remain unchanged. You will get a new form of the action typically, and then what you will end up getting is you will end up getting that this point P that you start off with will move to a new point which is called P of s, and from here we can actually calculate what is called as a beta function, which is the differential version of this RG flow. It is a differential version of this RS. So I can find what is the tangent to the trajectory in the flow line by finding this beta p, which we can actually compute. And how do I find the fixed points? If I know this beta p, then I just said find those points where beta of p star is equal to 0, and that will give me the fixed points of the renormalization group. So this is the idea: integrate, rescale, renormalize, and you will get the new coupling constants. So this is the mantra, if you like. So yes, I hope you are not overwhelmed by this, but let us continue, and you will see that the ideas are actually very simple when you look at an example. Okay. So what is a theory we can solve exactly? What is a field theory we can solve exactly? So it is the Gaussian theory. We have actually solved this exactly in the course before. So what we are going to do is we are going to start with the Gaussian theory, and I will show you in the lecture today that we can compute RS for this theory exactly, and we can also extract all the information by the same procedure of the renormalization group and compare it with exact results. Okay. So I am going to start with the ON symmetric Gaussian action. So what I have is I have an n component vector field, that is my field, and I have a d-dimensional continuum arena, and my action is given by this Gaussian theory. Now you see this has a coefficient of 1, so 1/2 del phi whole square, so that's like the term that was the Ginzburg term, if you wish. And then there is a quantity which we used to call T, but now you see that it has picked up something called TP. You will see why it is called P in a minute, and multiplying phi square. So this is a quadratic theory in that the fields appear only as quadratic terms, and therefore this theory is actually solvable exactly. Now we are working in the continuum arena, and so the Fourier transform is actually a continuum integral. And if I think of the field at phi of x, then it is the Fourier transform of the Fourier coefficients phi of k. And remember, this is where the cutoff comes in, and the cutoff is all the momenta within the momentum radius of lambda, capital lambda. There are no momenta above that radius, and this is what is telling us our theory has fluctuations in our theory cannot be shorter than this L scale that we have. So L is lambda inverse, and that is why we have this momentum cutoff that we have. Okay, so what is the next idea? So again, I should emphasize that we have written this in the continuum. So already anticipating that if it didn't work in the continuum, then this will not work, okay, because then the free energy will be continuum and infinite system. So that is also important. We will see that where that shows up. So we have solved this problem before, and so let us recall what we learned. Okay. So we know that this Gaussian theory has a finite correlation length. So that means if I simply compute the expectation value of some fields at two different points, different components, then we see two things. First is different components are uncorrelated. So alpha and gamma, there is a delta alpha gamma, which tells you that only the same component, ON component, is correlated with the other ON component. And the second point is there is a length scale, emergent length scale in the theory, which is this quantity, which is C, which is 1 by square root of Tp, right? And if you are on scale smaller than this correlation length, then the system looks like having power law correlation. So you see, so that it goes as 1 by distance between the 2 points to the power d minus 2. Whereas if you are on scales much larger than xi, then you will see that this system has exponentially dying correlations. So that is what is governed by this. And so on some scale of smaller than xi, it looks like a power law system, and on scales larger than c, it looks like a system with short range correlations, if you wish, by correlation length of xi. So this is the physics. Okay. Now what we know is that so this should be Tp equal to 0, apologies. So if this Tp goes to 0, then we know that C diverges, and then what we have is that this whole regime is of no meaning, because if C diverges, then any finite distance is of course much smaller than C, and therefore you will have power law correlation on all scales. Now we know that if we have power law correlations on all scales, then that system can be thought of as scale invariant, right? Because if you do a scale transformation on that, you can rescale the coefficients. That's what I am pointing out, is that the correlation function is a generalized homogeneous function, and therefore one can anticipate that the system has scale invariance. So we already know that if I put Tp equal to 0, this theory is a scale invariant theory just from this physics discussion. So this is what we want to think through, and we want to formulate the renormalization group Rs in such a way that we will recover the scale invariance back when Tp is equal to 0. Okay, let us see how we will do that. As I just pointed out, if C diverges as Tp goes to 0, we will expect that the theory with Tp equal to 0 will be a fixed point of the renormalization group. This is what we want to expect. So I am making this assertion on physical grounds. I know that this theory should have scale invariance on the fact that they have power law correlations and etc. And so we expect Rs of Sg, this Sg theory is theory with Tp equal to 0, right? And the reason for choosing the coefficient of this del phi whole square term to be dimensionless is anticipating that this is going to be a scale invariant theory. Okay? So the idea is that if we go through this Rs process that I described a couple of slides back, then this coefficient 1 is supposed to flow to some other value which is S dependent, but we will not want it to flow because you want to get back the same theory. That is what the fixed point of Rs being Sg equal to Sg, that this statement means. Okay, so we expect to get back the same coefficient. So that means I know that the action, because the partition function is e to the minus action integrated over all field configurations, this quantity should be dimensionless. Now the fact that this quantity is dimensionless will allow me to conclude that the dimension of the field is length to the power minus d minus 2 by 2. This is very straightforward from this expression. Okay, that is the dimension of the field at this Gaussian, in this Gaussian theory. Now what am I doing? I am perturbing that fixed point with a non-zero Tp. So I am adding to this theory a Tp by 2 phi square. Okay? So what will I find? By realizing that this field has dimensions of L to the power minus d minus 2 by 2, I will be able to conclude that this Tp has dimensions of L to the power minus 2. So now you understand why I chose the notation Tp, although I made a couple of typos here which I will fix. Tp is chosen to say that it is an object with some physical dimension, right? That is why we chose Tp, and it has dimensions of L to the power minus 2. So what I want to do really is I want to work with dimensionless quantities. So how do I introduce a dimensionless coupling constant associated with this Tp? So there is a natural object with some dimension lying around, and that is the cutoff. So you see it goes as L to the power minus 2. Therefore I can say that Tp is some dimensionless quantity little t times lambda square, length inverse square, right. So I am now characterizing this term by little t, which is a dimensionless coupling constant, times lambda to lambda square. So this is why we introduce this notation Tp, so that we can later replace it by a dimensionless coupling constant times lambda square. Now you can imagine that if I had a more complicated theory, and I could have many other terms like phi to the 4, phi to the 8, some gradient phi to the 6, something, all kinds of terms can be there. All their coupling constants can also by dimensional analysis be written as dimensionless quantities times some power of lambda. Okay. So lambda is not just the cutoff of our system, in some sense it is also the natural unit of measurement, if you like, right. It is just a way of thinking about it. Okay. So this is what we have achieved by observing this fact here, that Tp is a dimensionful quantity and that we can express it in terms of a dimensionless parameter little t and some power of lambda. So with this perspective now, we will agree that all coupling constants in the theory will be expressed in dimensionless language, and the set of points, the point P that we talked about, that point will have all the parameters associated with that point will be dimensionless. In this case there are two parameters, one is the coefficient of this gradient phi square, and this t, which is dimension Tp lambda square, so this t is that parameter, right. So one is the coefficient of 1/2 grad square and t lambda square is the coefficient of phi square, so we just keep the dimensionless parameter here. So the natural question now is, if I perform RS on this theory, what will be the new theory that I will get? That is the question. Okay, all right. So with that setup, what I am now going to take you through is I am going to take you through the 3 steps of Wilsonian renormalization group. So I start with this theory which we have now written out in detail, and so t is the dimensionless parameter and the partition function is path integral or the functional integral over all possible field configurations of this action. And our goal of course is to obtain RS. So the first step, as we recall again, is integrate. So what we are going to do is, we are going to take this momentum space and split it up into 2 regions. So region between lambda by s and lambda, so this correspond to short wavelength fluctuation modes, and there are longer wavelength fluctuation modes whose momenta are less than lambda by s. So how do I think about this in momentum space? So if you think about this as the momentum space, this lambda radius is the cutoff. So there are no momenta above that in our fields. That means there are no fluctuations on scales smaller than inverse lambda. That is what we mean. Now what we are going to do is we are going to take the modes that are lying between lambda by s and lambda. So that is this light orange kind of color. Those are the short wavelength modes, and we are going to separate them from the ones that are the longer wavelength modes whose momenta are less than lambda by s. So how do we achieve this mathematically? Well, it's very straightforward. So if you take the field phi of x, you see that phi of x is an integral over all Fourier components inside this inside this sphere, if you wish, in d dimensions. All of these momenta are included in that. Now what we do is we split this integral into this sphere, the blue sphere, that gives us the less than field. Less than fields meaning the fields with longer wavelength Fourier components. Okay, and this are the highly fluctuating fields with shorter wavelength terms. So we just write this is an exact splitting. There is no approximation here. This is an exact splitting. So we are saying that this field phi of x can be thought of as a long wavelength piece and a highly fluctuating piece. Okay. So as is stated here, phi greater than describes the short wavelength fluctuations and phi less than are the long wavelength fields. Okay. What do we like to do? we would like to integrate out these modes, okay, and that is where this integrate story comes up. So that's the first step now, to integrate. How do we integrate? Okay. So the goal of step 1 is to obtain an effective action only for the phi less than fields. So I am going to integrate out the phi greater than fields and get an effective action only for the phi less than fields. Remember, just recall what we did in the real space method. We integrated out the odd spins and got an effective statistical weight for the even spins. It's exactly analogous to that. What we are going to do is we are going to take this action, we are going to integrate out the phi greater than modes and try to get an action for the phi less than modes. Okay, and this is just notation, this is some intermediate notation to say S less than, means it is the action associated with the less than fields. Okay, now the partition function is this is an exact result, there is no, this piece is exact. And now what we are going to do is we are going to take this d phi and write it as two differentials. So it is like you are saying that something is a sum of two things, and therefore I am going to integrate, and they are like independent terms. And so you are going to integrate d phi less than and d phi greater than. Now remember how we defined this functional integral. The functional integral was defined as integral over the Fourier modes. So this d phi less than is the integral of the over all Fourier components less than the lambda by s, and this is the integral over all Fourier components between lambda by s and lambda. That is what we mean by this. And this action now I am writing as, recalling that phi is equal to phi less than plus phi greater than, I am writing it as a functional of the sum of these two things. Okay. Now what I will do is I will take this piece and I will first perform the integral on phi greater than, the functional integral on phi greater than, I will perform that. When I perform that, I will get an answer which I will write as exponential minus s less than phi less than, and that is the definition of s less than phi less than. Okay. So this is what happens here. Alright, now how do we do this? For this Gaussian theory, it turns out to be extremely simple, and there is an important thing that happens in the Gaussian theory. If I take s phi less than plus phi greater than, it turns out to be equal to s of phi less than plus s of phi greater than. Now what do I mean by this? That means that the original theory had, you have to put phi here, you have to put the phi here and phi here. So now if you take this phi, you have to write it as phi less than plus phi greater than. So if you simply expand, you will see that there are cross terms. There will be like, for example, phi square will have phi less than dot phi greater than 2 times, there is a number like that. But what happens when you integrate that out? So here is a very nice exercise for you to do, it is a very simple exercise. You will be able to see that the cross terms will just vanish, and I have given a hint, that is because plane waves with different wave vectors are orthogonal to each other. That is as simple as that. And because of that, the short wavelength modes and the long wavelength modes quote unquote do not talk to each other. Because they do not talk to each other, their energies will, or their action will split out, and you will get that this action is s of phi less than plus s of phi greater than. So this is what you will end up getting. Okay, very nice. So let us proceed. So I have made this observation. Now I am going to do the integration over the greater than modes. Because it is e to the minus s phi less than, this piece does not depend on the phi greater than mode, so you can pull it out, and that is what is done here. And now what you do, when you integrate this, you will get some number, and okay, it might even be infinity, but do not worry about that now. So we will just write it as e to the minus some number, right, e to the minus some number. Okay. So we should strictly call this less than, because it is going to be associated with this less than modes. So just there is a small typo here, and it is just notation, you can call this e into 0 less than. you can call it anything. It's like what it's going to do is you will find that this term will simply shift this action of phi less than modes by some constant. But this is exactly what happened in the Ising model as well. You remember that we introduced some constant shift of energy, and that once we integrate out the odd sides, you saw that energy shift also changed. Therefore, we know that the shift of energy is a completely innocuous thing. So, we can just drop it, and it will only contribute to the analytical part of the free energy. So, we can just drop it altogether. We won't worry about it. Just like we didn't worry about the shift of energy when we performed the fixed point calculations in the real space method. So, if we agree to drop this because it is uninteresting and it will give you some analytical piece, then you will see, based on our definition, that S less than phi less than is, in the case of the Gaussian theory, S of phi less than. So, the new action is exactly same as the old action. But unfortunately, we cannot compare this S less than phi less than theory with our original theory S phi. Reason? Our cutoff has changed. We have integrated out between lambda by S and lambda, and therefore we have a theory with a different cutoff. So, we can't compare these two theories. But what we have achieved is we have achieved to integrate out the fluctuating modes, and in this case it produced nothing except a shift of energy for the longer wavelength modes, and therefore didn't affect them at all. Nevertheless, you got a theory with a different cutoff. So, that's how you achieve the first step of integrating out the short wavelength modes. Okay, we are ready to implement the second step of Wilson's renormalization group, which is rescaling, or affecting the scale transformation on the coordinates and momenta and defining new fields associated with all the new quantities that come out of the scale transformation. Okay. So, the scale transformation is typically called rescaling. So, it entails three things. So, the first thing is the coordinates are changed. So, x becomes x new and the old x is divided by s. So, if s is, let us say 2, what was 2 meters now will become 1 meter, right. So, what was 2 meter, if it becomes 1 meter, I have zoomed out, that is what I have done, right. Think of a map, right. Mumbai, Bangalore is, it'll on a map will show up as a few centimeters, but it's hundreds of kilometers, right. So, something like this. Okay. Scale the momenta. How do you scale the momenta? In opposite way as the positions. So, the new momenta will be s times k. Now, why is that? How you motivate that is, so suppose I had an original plane wave. After scaling, the phase associated with the plane wave should not change. So, that is e to the I kx should be same as e to the I k nu x nu. So, if x nu goes as x by s, the natural way to get k nu from old x is to scale x by s. So, that is k nu x nu is equal to sx. So, what does this do now? Remember, now lambda by s, which is the new cutoff, when I perform the scale transformation, will go back to lambda. So, I have restored this system. Now, here is where the importance of having the thermodynamic limit comes up. So, suppose I took a finite volume system, then all of you remember that inside the in the momentum space, your momenta will come in discrete points, and the points will be separated by 2 pi by L, where L is one side of the system. So, each point in k space in each direction, coordinate direction, will be separated by 2 pi by L. And there will be a maximum cutoff which is determined by lambda, and so there will be a finite number of k points within this, albeit very large, but finite number of k points within this lambda radius. Now, if I do lambda by s and integrate out all the modes between lambda by s and lambda. I will integrate out all the modes, but if I now rescale, the number of modes remaining between lambda by s volume will be fewer. Or when I rescale, what happens is my lengths will change. What I am doing is I am changing the volume of the system to v by s, and therefore the number of momenta inside my new shell will be smaller. And if I keep doing this, ultimately I will have nothing left, right? And this is what we mean by saying that the phase transitions are associated with thermodynamic systems and thermodynamic limit. So you have to work in the continuum so that when you rescale in the momentum space, all the momenta within all the possible momenta in this in the shell are included. Everything inside, all possible momenta are included. There is no discreteness inside here because of finite volume, and because that when I rescale back, it's like stretching, it's like stretching a solid sphere or something, right? And then you'll get all the points back. And this is where the thermodynamic limit is used. Okay, so that's what happens. So I restore back the cutoff, and now I am going to define a set of intermediate new fields. Okay, so this is why I call it as phi tilde new in terms of the new coordinates. So this is a new field. How do I get the new field? The new field are only the long wavelength pieces, right? Because I have integrated out the short wavelength mode. So I have phi less than, and to find out what is the value of the field at x nu, what I do is I find out what is the original coordinate which came to x nu. So that is s times x nu, and I take the value of the long wavelength piece of the field at that point, and that is s times x nu, and that is how I construct this intermediate field. Now you will see why in a minute, why I call this intermediate. Now what I am going to do is I am going to take this effective action which I wrote down in the last slide. Okay, there is an unfortunate typo here, so this half should not be here, right? And so what you will do is you will see that you will have an action written in terms of the phi less than fields. Now what I am going to do is I am going to write all the quantities in terms of s tilde nu. So this is the intermediate action, and this should be phi tilde nu because that is the intermediate field. So I change d dx to the new coordinate. So what will that be? That will be d dx s to the power d, and this gradient I write in terms of the new gradient with respect to the new coordinate. So I will get s to the minus 2, this 2 powers of gradient will show up here, and phi less than x is literally equal to phi tilde nu x nu. So we write that down here, and I get 1/2 t lambda square and this term. So now you see I have an action of s tilde nu of this intermediate field phi tilde, and this looks like a completely different theory with different kind of coefficients, but remember it has the same cutoff lambda as we started off with. Now I want to use the fact that my Gaussian theory with the coefficient 1 is to be a fixed point of this renormalization group transformation, and this gives rise to the third step where I am going to impose the renormalization condition, and the renormalization condition in this context of this Gaussian theory is to say that in the absence of t, that means if I put t equal to 0 or Tp equal to 0 in the Gaussian theory, I will get Sg as my action, and that Sg which we defined before has to be a fixed point of renormalization group, which means under the scale transformation it should come back to itself. Okay. So if t is 0, s nu is not the original s, and this is not desirable, right? So if you look at, even if I put t equal to 0, I will see that it is sd and sd minus 2 and all this stuff is there. So it is not same as what I started off with. So this is where I am going to use a renormalization factor on my fields, and I am going to define new fields. Now this is my legitimate new field, How am I going to define the new field? I am going to say that the old field is a factor zeta of S times the new field of X new actually. And zeta of S is called as the renormalization factor. How am I going to determine the renormalization group factor? I will demand that the coefficient of gradient phi square after I introduce this renormalization factor on the field will return me back to unity, which is what I start off with, okay. And it is a very simple exercise for you to show that if you choose this condition so that the coefficient of this term is actually 1, right, is unity, which is what S had, this renormalization condition will give you that zeta of S is S to the power minus D minus 2 by 2. Okay. So, if I now choose that zeta of S to be that, now you see I get this S new, so it is a new action because I have done the scale transformation of phi new. So, all the intermediate terms have gone away, and you see I get a theory which 1/2 gradient new, phi new and all of this stuff, everything is as expected. The only important thing that happens is T changes to T times S square. Okay. So, that is what happens. So, let me just quickly revise what is the renormalization condition. So, we have these intermediate fields which we used by transforming the coordinates and defining new fields from the phi less than fields. We multiply our actual new fields we want with a scale with some kind of renormalization factor which we call zeta of S, so that the coefficient of this gradient new phi new of X whole square turns out to be unity. We demand that because we want the renormalization group transformation at t equal to 0 to leave the purely Gaussian theory of 1/2 gradient phi square to be invariant, because that has infinite correlation length as we know. So, what this gives is, it gives us Rs of S is S new, and that means that Rs of P, which was 1t, will go to 1t times S square. So, t changes to a new value, but this coefficient of gradient phi square does not, and we designed the Rs to get us the fact that Rs of this 1 will be 1. That is the renormalization condition. And now you see this remarkably beautiful result. It is kind of trivial at this stage. If I put t equal to 0 to start with, I will see that Rs of Sg, which is the theory with t equal to 0, is actually Sg. So, Rs of P10 will be 10. Okay. So, I have recovered a way of, I have recovered the Gaussian theory with infinite correlation to be a fixed point of this renormalization group transformation. So, I have actually constructed Rs to do this. Okay. So, this is where we are. Now, let us analyze this flow that has showed up in this parameter space of P. So, you see the Rg beta function, we have obtained the P of S, and this is just a formal definition. P of S is 1 comma T of S, and T of S from the previous slide is same as T times, where T is our initial value that we start off with, times S square, right. So, T is the value and S equal to 1 when we did not do S equal to 1 means we have just starting, we did not do anything to the starting theory. So, if this is the formal definition of the beta function, and now you will see that of course 1 will not flow, and this quantity here is S dt by ds is 2 times T of S. Okay, what is this 2? You see that 2 is just this, the square 2 here. Okay, so that is when you do S d by ds, you will see that that 2 will just come down. And you see this 2 here sitting in front of this is actually mu t. Okay. So, it turns out that people from condensed matter particularly would like to think about this somewhat differently, in slightly different parameterization if you wish. So, you actually define S is equal to e to the power L. so that this logarithmic kind of derivative is made into a simple derivative with respect to L, and instead of writing it as a function of L, you write it as S, you write it as a function of L. So little l equal to 0 is S is equal to 1, and therefore this equation, which is typically called as the renormalization group flow equation, is dt by dl is 2 times TL, and the initial condition for starting where we start our theory is T of 0 equal to T. Okay. Okay, I'll just make a brief comment here. So there is a version of this kind of beta functions that you have. They are called Kalan-Zimanzik equations in field theory. The conventional way of doing Kalan-Zimanzik equation will get a negative sign for this because their flows are towards ultraviolet, whereas our flows, the ones that we are discussing here, are towards infrared. So that's just again a convention, not a great thing to, nothing much to worry about there. Okay. Alright, so now with all this information, let us try to understand the critical properties of this fixed point, which is P star G. Remember, P1 comma 0 is a fixed point. How do we see that? So we know that it is a Gaussian fixed point, but we can also see that by saying that the RG equation, if I put the right hand side of this is equal to 0, you will get T of L equal to 0, and that is if the starting point, if the starting T of 0 was 0, then it will not flow. Okay. So that is the idea, and you will see that mu T equal to 2. Now before we proceed, I would like to suggest that you do a certain exercise so that you will get familiarized with this. So remember that this Gaussian theory we started off with and perturbed by this T lambda square by 2. We had ON symmetry. So suppose you introduce a symmetry breaking field, and the symmetry breaking field has some physical dimensions. So I am going to write it as HP times E. E is some unit vector in the ON space. So HP E dot phi of x. Okay. So your first exercise should be to show that this HP can be written as H times lambda to the power d plus 2 by 2, and therefore you will have to do some dimensional analysis to get to that. From there you go through this RG process that we have done, and you will see that the point of this theory, which is 1TH, 1T and H is dimensionless written here. Under renormalization group transformation, we will go to 1T of S, H of S, where this is T S square H S to the d plus 2 by 2. And from there, in addition to this RG equation which we had already derived, you should be able to derive a flow equation for this H, dimensionless H, and you will also see that this tells you that mu H is equal to d plus 2 by 2. Okay. So please try this out maybe after listening to this lecture. So I am going to use all this information now. So you now see that there are two relevant operators near this critical point, this Gaussian critical point that we have. Both mu T and mu H are positive. Mu T is 2 and mu H is d plus 2 by 2, both are positive, so they are relevant operators. And so based on our discussions of the general formulation of renormalization group, we see that this free energy density as a function of this dimensionless parameters T and H is going to be a generalized homogeneous function, right, in this fashion. This is what we discussed. Once you realize this, you can pull out all the critical exponents. So alpha is 4 minus d by 2, gamma is equal to 1, nu, which is the correlation length exponent, is half, but that we already knew from the analytical result, so it's not a big discovery, but it's showing us that it's consistent. You will see that delta is d plus 2 by 2 by d minus 2, so this is what you will find here, and eta is equal to 0, and important thing is that we don't ask what is beta in this because it's a little unphysical to ask that, because we don't have any quartic term in phi and so on. So I cannot ask what happens to the theory when t is less than 0, then I will get into some difficulty there. So it gives an ill-defined theory, so we will not worry about that. And important thing to note is that these exponents like alpha, gamma and nu are exactly what we got from the saddle point approximation of Ginzburg-Landau theory. And remember, in the saddle point approximation of the Ginzburg-Landau theory, let us say above Tc, where little t was greater than 0, the theory looked exactly like this with some coefficients that were differently labeled. And now you can see that we have actually, whatever we did explicit calculations to get alpha, gamma and nu, etc., we are able to obtain that without actually doing those calculations, but from very general arguments based on scale invariance about the Gaussian fixed point. So in a sense, we have recovered known results from the renormalization group. Okay. Now I turned on the field and I got all the critical exponents for you, but I want to take you back to the system which has the ON symmetry. So let us set the H back equal to 0. So we know that t equal to 0 is the Gaussian fixed point, but I will show you now that there is another fixed point. What is that other fixed point? So remember the RG flow equation, which is that dt by dl is 2t. Suppose I define a new variable called y, which is 1 by t. So you will see that this equation will get d, if you just go through the algebra, you will find I define this variable and I get this differential equation. You will find that dy by dl is minus 2 times yl. And suppose I ask what are the fixed points of this flow, I have to set yl equal to 0, so I will get y equal to 0 as the fixed point. But what is y equal to 0? Y equal to 0 is t equal to infinity. Now what does t equal to infinity mean? Recall that the correlation length went as 1 by square root t. So if t goes to infinity, that is talking about a system with 0 correlation length. That is our paramagnet, the infinite temperature paramagnet if you wish. So there is another fixed point lurking around which was not obvious, if you look at the equations it is not obvious, but it is clear that it is there from this analysis. And you will see therefore that this paramagnetic fixed point is P star paramagnet has 1 is the coefficient of the del square and infinity as the coupling constants. And this gives 0 correlation length, which is again RG invariant, because if I scale 0, I will get 0, right. So that is the idea, okay. So this whole story can be nicely described in RG flow diagram. So this Gaussian theory that we wrote down has the critical 1/2 del square theory, which is perturbed by t, and as in the t space I have drawn it on a finite line. You should imagine that there is an unstable fixed point here. If I have a finite t, it will flow, it will keep flowing. It is pretty much like the 1D Ising model, although the critical properties are very different. And then it goes to t equal to infinity, which is the paramagnetic fixed point with 0 correlation length. I mentioned the 1D Ising model. You may wonder why it is not coming out as t equal to 1. That is because the t definition in the 1D Ising model is somewhat different from the t definition here, but conceptually it is the same thing in terms of the flow structure of the flow. So you start with an unstable fixed point at t equal to 0 and you go to some a stable fixed point, which is like the paramagnetic phase if you wish, at very high temperature if you wish. That is the idea. Okay, this flow shows that t is a relevant operator here and an irrelevant operator here, and that is why I called it the paramagnetic phase. So there is no symmetry breaking, there is no symmetry preserving relevant operator around this. Okay, very good. Now I want to show you this power of this renormalization group idea and the concept of the renormalization condition by recovering the paramagnetic fixed point by another way of performing the renormalization group calculation. So what I want to aim for is, I want to aim for studying the paramagnetic fixed point. So how do I do this? So I define the theory in a different way. I define the theory by a different set of coupling constants. So I start with S of phi, which is d to the d. Now I have a dimensionful coefficient, that is why it is called yp, to say it is it has physical dimensions, and del square, and now what I do is I keep the coefficient of the phi square term to be 1. Okay. Now yp is a dimensionful coupling constant as we just saw. The theory has, let us say, the same cutoff as the other theory that we start off with, and in this form, because I am keeping this coefficient to be dimensionless, you now see that in this theory phi has a different dimension. So phi of x is L to the power minus d by 2 here, and yp will have dimensions of L square, and therefore yp can be naturally written as a dimensionless coupling constant y and lambda to the minus 2. So in this way of parameterizing the theory, the point P will be called y1 because y is reserved for the coefficient hitting the del phi square term, and the 1 of course is hitting the phi square term, and that is why I am writing it as y1. Okay. Now I invite you to go through the 3 steps, namely integrate, rescale and renormalize, and I will jump to the point of what I want, and I want to emphasize what should be the renormalization condition. To see what should be the renormalization condition, you will see that this correlation length C will satisfy lambda C. Okay, there is a small error here. This should be square root of y, not y. It should be square root of y because this has dimensions of length square. So lambda C should be square root of y, implying that y equal to 0 is a theory with 0 correlation length, right. Okay. Because it is 0 correlation length, it should be fixed point. So what I want to do is, I want to implement renormalization group now with a different renormalization condition, which is that the coefficient of the phi square term should be left as identity, as the number 1. Okay. So if you follow the 3-step RG process and demand that the coefficient of half phi square term, this 1 is kept unchanged under the RS transformation, so that when y, the dimensionless coupling constant y is 0, I get the fixed point as the paramagnetic fixed point. And now you will find the zeta of S, the renormalization factor that you need to define the new fields, there will be different from what you had at the other way of parameterizing the theory, and you will see that this will go to S to the minus d by 2. And the upshot of this whole thing is that resulting Rs of P, which is now defined as y1, is actually ys to the minus 2 comma 1, whose RG equation is d by dl of yl is minus 2 yl, which is exactly what we had derived using the this transformation that we did of y equal to 1 by t. And now you see at y equal to 0, this gradient operator is actually irrelevant, and that is what we also saw in the RG flow equation. So this y star Pm equal to 0 is a stable fixed point in this picture, because if I have a small y, then it will flow back to y equal to 0, and P star G can be viewed as the fixed point where there is another fixed point of this RG flow equation where yg is infinity, and that is an unstable fixed point in this picture. So hopefully you see the idea of what is the renormalization group, the renormalization condition that we need to determine zeta of S. So zeta of S will be determined by, definitely you need some physical insight into the problem as to what fixed point you want to study, and you have some idea about the properties of that fixed point, and you use those ideas to come up with what zeta of S is. Okay. So this is the framework of renormalization group, and I hope you see that it's quite powerful, because simply from the fact that we did a lot of very detailed calculations to find out alpha, gamma and all of those things for the Landau-Ginzburg theory in the Gaussian approximation. But here, by simply doing scaling and by doing this RS transformation, we are able to simply find mu t and mu h, and from there just get all the results. This we can do for the Gaussian theory, and we can also do this for other theories, and that's what is the interesting aspects of this, and that's why this method of Wilson is actually very powerful. Okay, so I hope that you found this lecture exciting. So it might be a good idea to just revisit all the ideas we have seen in this lecture. So we'll start with some kind of ON theory defined in the continuum, and the theory itself can be thought of as some point in a space of theories. Wilson's idea, essentially to put in a nutshell, is to correctly describe the physics of long wavelength modes, and in particular ask what is the effect of short wavelength modes on the long wavelength modes, right? And this is achieved by taking the field and splitting it into long wavelength mode piece, that is phi less than, and short wavelength piece, which is phi greater than. You integrate out the phi greater than modes, that will give you a new action for the phi less than mode. So this changes cutoffs, right? So that is the integrate part. Now we rescale. When we rescale, we restore the cutoff back to the original value, and we renormalize. That is the third step. We define the new fields with a scale with some renormalization factor zeta of s, and zeta of s is chosen to reproduce some known fixed point that you are working around. Okay, and this will fix the all the parameters that are required, and you will get a new action, and the new action typically will have the same form as the old action, and you will see that RS will therefore produce a set of new coupling constants which are S dependent, and by analyzing those coupling constants we can actually find the beta function, and when you write down the beta functions, as I showed you, the coefficients of certain terms will actually be the dimensions of the dimensions. I mean, by that I mean the exponents mu t and mu h, etc. At least in the Gaussian case they will turn out to be exactly what are there. In later examples we will see that there are some more bells and whistles to be dealt with, important ones. Okay, so that is what you will get, and what we did was these ideas that we had, we demonstrated them by explicit calculation of the Gaussian model, where the RS can be implemented exactly. There is no approximation of any kind in implementing RS for the Gaussian model, and we were able to obtain the two fixed points, namely the Gaussian critical point and the paramagnetic fixed point, the paramagnetic phase, and we were able to extract critical properties near the Gaussian fixed point, which agreed with our explicit detailed calculations that we did using the Ginzburg-Landau theory within the Gaussian approximation. Okay, so that should be a lot for one lecture, but I hope that it's useful. So I would encourage you to sort of work through all the details yourself, try to do these calculations in your own way and understand it and sort of internalize these ideas, because these are extremely important ideas if you want to do research in physics. And you will see that these ideas are also far pervading, as we will see later in the course. So what will we do in the next lecture? So you saw that we got some RG equations, and there was some apparent magic where the coefficient of the RG flow equation turned out to be mu t and so on. So we will see why that is the case. So we will try to understand those results a little better, and naturally we know that this Gaussian fixed point is not describing the critical point between, say, in the Ising magnet or in some ON magnet. It is not describing that, because we know those exponents are not what we that are known from either numerics or experiments or whatnot. So clearly we have to work with a more richer theory. In fact, we have to work with the ON Ginzburg-Landau theory, where there are other terms like the phi to the 4 term, etc. So that is what we will do, and we will see that conceptually, although the framework is exactly the same, technically that problem turned out to be far more challenging, because you have to invoke a variety of techniques from field theory to do the calculations, because the theory is no longer Gaussian in the sense that there are these quartic terms in the action which will spoil the the advantage of having exact solvability. So that is what we will do, and I am sure that you will want to know about all this. So I will see you in the next lecture. Thank you and have a nice day.